All right, so now we move on to our final test here, test 5, dealing with these log and exponential functions and our inverse trig functions. So first we talked about the log function. We talked about derivatives with the log function. So we talked about the natural logarithm, and we developed, of course, that the integral of 1 over t dt is the natural log function, so that the derivative of the natural log is 1 over x. The derivative of the natural log is 1 over x. And we reviewed, of course, our properties of logs, which we can use oftentimes to simplify some expressions with logarithms. Right. Specifically, if we had this function here, log of square root of x plus 1, right, we, doing it the long way, would do the derivative of the inside function and then follow the rule for log. It's 1 over the function times the derivative of the inside function. Or, we can just do it with properties of logs. Right, so log of square root, we can write that as 1/2. Property of log says we can multiply the exponent out. We then just have 1/2 ln x plus 1. So it's 1/2 times 1 over x plus 1 times the derivative of x plus 1. So we get 1 over 2x plus 2, the same answer, far quicker using our properties of logs than if we try to do it directly. And of course, if it's even more complicated, it's the case as well. So you'll have some problems where you're doing derivatives with logs, and some of those will require you to use your properties of logs to break the log up first before you proceed to do the derivative. So look for some problems dealing with derivatives with the natural log function. The second thing we did is integrals that worked with the natural log. So one of the other things we talked about with logs before I get into that was this process of log differentiation. That's applying a logarithm. So your option here is to do your quotient rule along with the chain rules for both parts, and that'll work. Or we can do what's called logarithmic differentiation. Logarithmic differentiation. We can use this process of logarithmic differentiation here. And that works really well if you're given these tower functions. Works really well. So in addition to regular differentiation, you may be asked to do logarithmic differentiation. And again, that works. It's kind of necessary for these tower functions to be able to do the derivative of these things. It can also be helpful, though, when doing the derivatives of kind of complicated product or quotient rules. And then integrals with log. Remember, 1 over u du is ln absolute value. So a lot of these involve using our substitution process, recognizing what u is and accounting for du so that we can carry the substitution through. So in particular, this is where we developed our rules for integral of tangent, integral of secant, integral of cotangent and cosecant, using the trig definition, and then some little tricks, of course, with secant and cosecant. So you expect to have some problems where you're dealing with some integrals that result in logarithms, or actually that may even involve a logarithm, like this example here. Okay, so look for integrals involving logarithms. We then moved on to our exponential function, e to the x. Remember, e to the x is its own derivative. We actually saw that a couple of ways, kind of implicit differentiation way here, as well as the direct derivative rule, kind of looking at what that limit approach is, although that's not an absolute certainty that we can be sure of that, but it does actually approach that. All right. And so then we looked at some derivatives with the E, both with the chain rule, also as part of product or quotient rules. We talked about derivatives with e to the x. We then talked about some other examples, increasing, decreasing, relative extrema, absolute max, absolute min. Any of those kind of questions we asked before could be, you could run into something like that. And then, of course, we turned around and did integrals with e. We did integrals with e. And again, that's following the basic substitution rule on the exponent, trying to account for that. So expect a couple of examples where you may have to do some integrals involving e to the x. Integrals involving e to the x. Okay. And then finally, we moved on to talk about our inverse trig functions. So we reviewed a little bit of the basic facts about inverse trig functions until we turned around and started doing derivatives of the inverse trig function. So we developed the rules for the different derivatives, and then we went through and did some problems involving the derivatives of these guys. And things like x arc sine of x or arctan of 4x. Yeah. So any of these kind of derivative problems, you could run into this kind of stuff on your exam. Okay. And that pretty much, and again, here we reviewed an example where we were once again finding increasing, decreasing relative extrema. Here is actually relative maxes and mins. Of course, we've talked many times about equations of tangent lines, so with any of these derivatives, you could be asked about finding the equation of a tangent line. Of course, we also did some implicit differentiation. So, of course, don't neglect that there could be something about differential equations. Could have one of those in there. Definitely probably something related to increasing, decreasing, a problem with that, absolute max, absolute min. Could be asked about equation of a tangent line. Okay, so you refer to those things in examples. Again, you have a set of practice problems up in the homework for the review. That should help give you kind of a feel for the kind of questions that you're going to run into. And again, if you do have additional questions, please contact me. Most important, show your work. That way, if you do make a mistake or two, I can go back and give you some credit for the problem.